Welcome back, everyone. So far in this course, we spent a lot of time talking about the derivative, about what it is, what it means in context, what it can tell you about the graph of the function, and so on. And we know that the way to find the derivative function is with this limit that you see on the screen. We've talked about this in the past, but sometimes actually evaluating this limit is not the most pleasant experience. And so the next block of this course is going to be discussing and discovering different ways to evaluate derivatives without having to go through evaluating this limit every single time. And we actually already know a couple of these shortcuts from when we were graphing the derivatives, and we noticed in that video that the derivative of any linear function is just the slope of that line, and the derivative of any constant function is always 0. And what this means is that if you see any linear function or constant function, you do not need to use the limit definition to find the derivative. You can just jump straight to the answer because we've already talked about it before. And just to demonstrate what I mean, let's say we have the linear function 3x minus 7, and I wanted to know its derivative. And being a linear function, I could think back to the previous slide, the derivative of a linear function is the slope of that line, which in this case is going to be 3. And that's it. That's the answer. We found the derivative. We don't need to do anything else. Now, if we wanted to, we could have used the limit definition and would have gotten the same answer, but it would have been far more work than necessary. And I'm not going to walk through that work because the whole point is that we don't want to do it, but if we did, there'd be a lot of algebra, a lot of things to keep track of, and a lot of room for error that we just don't want to deal with. But since this was a linear function, and the derivative of a linear function is the slope of the line, I can just know right away that the derivative in this case is 3. Now this shortcut only works for linear functions, and there are plenty of other types of functions out there. We have power functions and exponential functions and trigonometric functions and many more. And the next block of this course will be all about going through these different types of functions and seeing if we can find any shortcuts that will get us out of using this limit definition of the derivative. And in this video, we're going to get to 3 different types of functions. We're going to get to constant multiples of functions, we're going to get to sums and differences, which I kind of lump into one type, and we're going to get to power functions. And by the end of this video, we'll have a rule for each one of these that'll allow us to not use the limit definition. So let's start with constant multiples, which is whenever you take a function and multiply it by some fixed constant number. And when you do that, what happens to the graph is it either stretches or shrinks by a factor of whatever that constant is. And this will either increase or decrease the slope at any point by that same factor. And since the derivative represents the slope at any point, the punchline here is that if I'm taking the derivative of a constant times a function, that's the same thing as taking the constant and multiplying by the derivative of the function. So whenever I'm taking the derivative of a constant times a function, I can ignore the constant, take the derivative of the function, and then multiply by the constant at the end. Now this is different than when I take the derivative of a constant on its own, which we talked about earlier, is always 0. But this is not a constant on its own, this is a constant being multiplied by a function. Next, let's look at the sum or difference of 2 functions. And if I have 2 functions and either add or subtract them, and I look at the slope of that, the slope of a sum is the sum of the slopes. And essentially what that means is that if I have the derivative of a sum of 2 functions, I can take the derivative of each function individually and then add those together. Essentially, it's acting like the distributive property almost. I am distributing the derivative to each individual function. And the same thing is true with a difference of functions, where the derivative of a difference is the difference of the derivatives. Lastly, we're going to look at power functions, which is whenever you have x raised to some constant power. Now the background and intuition for this one is a bit tricky and might get us a little too sidetracked, so I'm actually going to leave it out of this video and just give you the rule instead. I'm going to leave a link down below to an excellent video by 3Blue1Brown that includes much better graphics than anything I could create, and he walks you through some of the intuition for this rule. Now the rule for this one is that if you have any power function x to the n, its derivative is n times x to the n minus 1. So you take the exponent, you bring it down in front, and then you subtract 1 from the exponent. As an example, if I were to take the derivative of x cubed, that's a power function with an exponent of 3. And so I bring the 3 down in front, and then I subtract 1 from the exponent, and so I get 3x squared. Now this derivative rule is often referred to as the power rule. I want to run through a few more examples of using the power function where some nuance can appear. Now let's say I want to take the derivative of 1 over x cubed. It doesn't look exactly like the right format from what I had on the previous slide, but keep in mind that 1 over x cubed is really x to the negative 3, and now it's a more obvious power function, and the way that I take the derivative of that is the same exact way. I take that negative 3, I bring it down in front of the x, and then I subtract 1 from the power. Just keep in mind that negative 3 minus 1 is negative 4, not negative 2. And then at that point you'd be done, but if you want to rewrite it to make it look a little prettier, you could rewrite that as negative 3 over x to the 4th. And as a side note, whenever you take a derivative, you don't have to simplify that unless we explicitly ask you to. Another example would be the derivative of the square root function, which once again doesn't immediately look like a power function, but remember back to pre-calculus that the square root function is really an exponent. This is x to the 1/2. And now that I write it like this, I can much more clearly apply the power rule. And when I take the derivative of x to the 1/2, I'm going to bring that 1/2 down in front. And then I'm going to subtract 1 from the power. And then 1/2 minus 1 is negative 1/2. And that's my derivative, and that's my answer. But I could rewrite that as 1 over 2 times the square root of x, because x to the negative 1/2 is a square root down in the denominator. And finally, let's look at the derivative of x to the pi. And that pi might look intimidating, but the way you take the derivative is the same thing as before. Using the power rule, you're going to bring that pi down in front, and then subtract 1 from the power, which is just pi minus 1. And so the derivative of x to the pi would be pi x to the pi minus 1. Let's recap all of the derivative rules that we've seen so far. So the first that actually wasn't in this video, it's from a previous video from this week, which is that the derivative of any constant by itself is equal to 0. The second is the constant multiple rule, which says that if I'm taking the derivative of a constant times a function, I can take the derivative of the function and then multiply the constant in afterwards. So I can kind of ignore it until the end. And again, this is different from the first rule because the constant here is not by itself, it's attached to the function, and so it's behaving a little bit differently. The third and fourth rules are the sum and difference rules, which say that the derivative of a sum or a difference is the sum or difference of the derivatives. So I can distribute the derivative to each function individually. And the last rule that we just talked about is the power rule, which says that the derivative of x to the n is nx to the n minus 1. And I'd recommend writing these down and leaving room for more because we're going to continue to add to this over the next several sections. Now you might not be using each of these in isolation. You might have to use several of these at once to find the derivative of a particular function. And let's look at one example of that. Let's say I want to find the derivative of the function 5x squared plus 3x plus 2, which is a nice polynomial, and you can find the derivative of any polynomial using just the rules from the previous slide. So first thing to notice is that this polynomial is a sum of 3 terms, and so I can use the sum rule to distribute that derivative and take the derivative of each term individually. So I'm taking the derivative of 5x squared plus the derivative of 3x plus the derivative of 2. And now when I'm taking the derivative of 5x squared, I can use the constant multiple rule to ignore the 5 and bring it out in front. And so my answer for that first derivative will be 5 times the derivative of x squared. And same idea for the middle term. I'm going to be taking the derivative of 3x, which is the same thing as 3 times the derivative of x. And I inserted that little 1 in the exponent just to really emphasize that x is a power function because it's x to the first. And then the last term there is the derivative of 2, and that's the derivative of a constant, and the derivative of constants by themselves are always 0 because they have a slope of 0. So from here, to find the derivative of x squared, let's use the power rule. So let's bring that 2 down in front, and then subtract 1 from the power. And so the derivative of x squared is 2x. And then same sort of thing with x to the first. If I bring that 1 down in front, this is 1 times x to the 1 minus 1, which feels a little bit silly because x to the 1 minus 1 is x to the 0 power, and x to the 0 is 1, and so actually the derivative of x was just 1. And now simplifying all of that, I get the answer of 10x plus 3. And so the derivative of 5x squared plus 3x plus 2 is 10x plus 3. And as you get better at this, you might not need to write out all of those steps, and that's okay. But when you're first starting, it might help to keep track of what rule you're actually using, to just use one rule at a time.